So how do you analyze a two-group within subjects experiment? The important part here is all the ideas are the same. The p-value, the 95 CI, the random sampling distribution, standard error, all that stuff's the same. It's slightly tweaked mathematically if you were doing this all by hand, but we don't have to. So I don't have to talk about any of the concepts, just how to do it. So our data is the same as last time, except I've presented it in a within subject style, 1 row per participant. Each participant gives me 2 scores, 1 in the music condition, 1 without music. Both of my columns mix IV and DV together, right? Each of the columns represent the IVs, right? So the scores for with music are in the first column, the scores for without music are the second column, right? So we got scores in both columns. We got an IV and DV kind of mixed, matched together. I do like the way between subjects, data just kind of has a column for the IV and a column for the DV, but that's not what we get here. This has not been standard practice in stats data entry for over 50 years. So it is what it is, but this is what it should look like. We want the p-value, the 95% confidence interval of effect size. Those are the 2 things I care about. Everything else I said holds, like I said before. So now I get into Jamovi, and I enter my data just like this. It's the same as what we saw, except I took the percentages out. I clicked on the music score variable, made sure to have no spaces, no special anything in there. Some of the Jamovi programs, if you want to do more advanced analysis, die and fail if you have a space in there. They're continuous. They're integer types because there's no decimals. It usually does this stuff automatically. But ultimately, I clicked on both of my columns, and I made sure they were both set to continuous. That's all you have to do. Click Analyses, T-Test, Paired Samples, T-Test. That's how we get the screen we need. So this is what your Jamovi screen will look like. If you look, the first thing I did was put in music scores first, then no music scores, because I was predicting that studying with music improves test scores. So I put that variable in first, and I put the studying without music. I thought that would have lower test scores, so I put that in second. If I do it this way, then if I get a negative sign, that means my hypothesis was incorrect in terms of direction. Now, I think that's cool, so you got to think about that. I like it when my negative T statistic and my negative D suggests that my effect is in the opposite direction from what I predicted. So that's what I'm doing here, and that's why my test statistic is negative and my effect size is negative and so forth. We'll get over there in a second. The options I need to click are students, effect size, the 95% confidence interval of effect size, descriptives, and descriptive plots. The other stuff was automatically chosen for me. You don't change that. It's no big deal. And I get a lot of beautiful things here. The first thing that I'm looking at is my plot. And you can see that those who studied without music did better than those that studied with music. There's my median in the no music condition is a little bit lower than my mean in that condition, suggesting there may be an outlier, a high-level outlier pulling those scores up. We'll look at this data another way, too, in a second. And then in the music scores, it doesn't suggest there's an outlier there. We'll get to that. I'll show you how to look at the outliers. I didn't use FlexPlot in this example because FlexPlot doesn't work with this example. I prefer to use FlexPlot just to look at my data first. But with this one, I had to run everything and get my data. But where I go to first is I want to understand the pattern in my data. And here, studying without music is better than studying with music, right? So now we're all good there. Let's go up to our paired samples t-test result. It's telling us that music scores minus no music scores has a student t of negative 8.946, so that'd be negative 8.95. My sampled mean difference, okay, my sampled mean difference, both sample means subtracted from each other, particularly music scores minus no music scores, is 8.95. Standard errors lower than the predicted mean difference of 0 if the null hypothesis were true. Our degrees of freedom are 4 because there's 5 pairs of observations. There are 5 participants. Minus 1 is 4. Don't worry about degrees of freedom. It's a throwback to the 1950s. We don't need to know it. We do have to report it. Our p-value is less than 0.05. This is a significant effect. We know that our independent variable has an impact on our dependent variable in the population. Our Cohen's d is in our sample, so that's just our sample Cohen's d. Not thinking about population, but in our sample, that is -4. Well, that's much greater than a large effect size of -0.8. So that is a large effect size in our sample. The population effect size is some number in this interval that ranges from -6.7983 to -1.217. Both of those are large. They're both greater in magnitude than 0.8 absolute value-wise. Descriptive statistics are what we're going to need to enter in our data. So ultimately, getting this output is super easy. We just ran a t-test. No problem. It takes a couple minutes. So I'd like you to check your data for outliers with the descriptive statistic, just kind of the descriptive statistics analysis option. Let's get a better sense of our data than the graph we saw before. So you click Analyses, Exploration, Descriptives. These options pop up. I put in both of my variables into the variables box. I changed my descriptives to variables across row because I think it's prettier. I clicked off a lot of options of the statistics. That's not it. The options underneath the statistics options are the plots options. I want my histogram and my density. We'll see what that gives us. That gives us these histograms with those density curves, which is just probability curves. And let's just say we're looking for outliers, okay? Or, bad data entry, things like that. And we're like, well, let's see here. Do we have any scores that are really uncommon? Well, these data sets are small. There's only 5 observations per group, right? So there's not that much data here. But we can see that, okay, maybe that 95 is a little out there, but it's not really a score. We talked about this last time. It's not really a massive outlier or anything that we should get rid of, but it's like, okay, it's a little different than the others. We can see that in the second histogram down there. Now, histogram is just a distribution of the number of observations that fell in a certain range. So, if we're looking at that bottom histogram, it's like, okay, there are 3 people scored between a 90 and 92. And there's like 1 person that scored between 87.5 and 90. And there's 1 person that scored, it looks like between 94 and 96 or something like that. But all we're looking for here is a massive outlier. We don't see a massive outlier down there. Up in the music scores condition, I don't see any outliers, right? And then those little curves that are put on top of it are just like allowing us to examine, well, are our data normal? Not really, but we don't have a lot of data. Do we expect anything better with 5 observations? The lesson here is we need more data, but this is how you check for outliers and normality. Yes, I'm going to ask you to do this on the test, but just to look at it. I guess it's not the end of the world. I just want you to look at it. Do you think you have an outlier or not? So I'll ask you that maybe as like a follow-up question, but it won't be part of our every time we do this analysis process. The one thing I do want to say about the difference between sort of lecture and lab is that I'm going to show you to do more things in a different way than lab does. That's part of my teaching philosophy with computer programs. I'm really good at them. People seek me out for advice on computer programs. I'm not really bragging here. But the reason how I get good at them is just by playing around with them. So this is one way to play around with it. Our write-up is essentially identical as last time. All the rules hold. The only things that really change are everything from my t-statistic out, and that's just because it uses a little bit different math formulas. And I didn't show you those today because you don't really need them. Like the t-test formula is a little bit different. It's instead of analyzing the individual observations, it analyzes the differences across the two conditions. Look, it's not a big deal, and I don't think you need to understand that. If you want, you can look up the formula yourself, break it down, and that sort of thing. That's something they'll teach you in Stats for Life Sciences, but honestly, to do analysis, it's just an extra burden. So, essentially everything's the same here. You're probably asking, why are the results different across the two t-tests with the exact same data? It's a great question. You have the same participants in both conditions, right? That's the difference. So you can mathematically remove individual differences. So you're probably like, well, how do you quantify individual differences? You just average each participant's scores together. So the participants with the highest averages are the best students. This is across both conditions, right? So it's like you're saying, oh, condition doesn't matter. If we ignore condition and just average scores together, who did the best overall or on average? And participants with the lowest averages across their two scores are the worst participants. You can mathematically remove this with complicated stats that we're not getting till the end of class. You just got to kind of trust me there. There's also something else that you got to understand. If individual differences matter in your data set, the scores in one condition will be highly correlated with the scores in the second condition. So you do want to check if individual different... Well, you don't have to do this. The computers do this. So this is like advanced stuff. This whole slide is just extra for you to know. But let's say you wanted to know, oh, did individual differences even matter in my study? Well, the math, what it does is it looks at the correlations between your two conditions. So if scores in your music condition are completely uncorrelated with scores in the no music condition, then individual differences didn't really matter for your experiment, okay? But the amount of the correlation between the two conditions is the amount that individual differences are contributing to the data. If you don't get any of this, it's fine. The reason why they're different is just because you have the same participant in both conditions. That's the difference. It leads to some changes in math. But if you're curious, like, oh, how do I find a correlation with Jamovi? I'll show you that later, more detailed. But analysis, regression, correlation matrix. Throw your two variables in at the top. And you can see that our two variables are correlated 0.6386. I'll explain what that means later. But essentially, that's telling us that individual differences did matter. People who scored better on the first test also scored better on the second test. But this whole slide is just kind of extra, teaching you extra stuff. If you want to know why do the two scores give you different results, it's because you have the same participant, and we can remove individual differences. And how do we do that? We find which participants had the best and worst scores, who were the best and worst students independent of condition, and we remove that from the analysis, so then we can find the pure effect of your manipulation. But that's it. Now, if you look in your t-test options, what tests you can click, you have something you've seen before, the Bayes factor, and something you haven't seen before, the Wilcoxian factor. Remember our assumptions: normality of the data. So normally distributed difference scores. So that would be no music minus music condition, or music minus no music condition, depending on what you predicted. Those are difference scores. So are those difference scores normally distributed? We also assume equality of variance or standard deviations across the two conditions. It's not really the end of the world, or not really a big deal there. The Bayes factor tells you the probability of the alternative over the probability of the null. And the Wilcoxian test is another ranked test that has no assumptions. So what we see here is that if this were my data, I would run the Wilcoxian ranked test, okay? And my p-value is not significant. And that would make me think, well, maybe there is an outlier in this data. Ultimately, it's not that non-significant. It's almost significant, right? But for me, when that happens, it's like, okay, there's some assumption that's a violation of my data that's causing my data to go from massively significant to non-significant. I should really run a better study. That's what I would get from this output. Now, these are optional. These are not required. This is just what I do in my own data practice. Now, I do like the Bayes factor, though. The Bayes factor, though, says the alternative is about 41 times more likely than the null. And if you were a Bayesian statistician, you would be like, this is great data, right? Like, Statistical analysis is one of, well, here's the numbers, and you get to make some choices that are reasonable with those numbers. For me, I want everything to show out. So I would love my Wilcoxian test to be significant, less than 0.05, my students to be significant, less than 0.05, and my base factor to look something great like this. If not, it's hard for me to draw conclusions other than maybe I screwed up. And that's how I do my data analysis. But this is not required. This is just Dr. D teaching you extra stuff. And then that's it. That's all we need. I gave you a couple really long lectures. That's not my goal, but sometimes it has to happen. Now I'm giving you a really short one. But that's it. Get the data, analyze it, write it up, and be done.